Now let's back to our slides, and we just have seen that this 2-bit addition no longer sufficient. We need to have something for 3 bits. So this 2-bit addition, we call it a half addition. Means we are just looking at the half of the scenario here. But full addition, we need to consider all the 3-bit, including the carry in on the stage. So my primary inputs there become like carry in A and B, operand 1, operand 2, and we take the sum and carry bit accordingly to the truth table. So I give some example here in the slide 2, and what we just have seen in the text typing I was making just prior to this, that should be sufficient for you to understand this concept. The second one is again looking at some example which we just did on the text file. It is explaining what is a no overflow condition and what is an overflow condition, etc. Now we need to see how we can make it logical. So we have truth table in our hand, and we have seen if I have a truth table, I can make a logic circuit out of it. So for the half addition, let's take this one, half addition truth table. So I have this circuit has two output, Y and Z. Let's consider Y. Now look at the Y table output. So it is like an XOR table, like XOR. If you go back to our digital logic gate discussion, you will see the XOR truth table exactly same as my output Y truth table. Okay, so it is basically Y equal to A XOR B, and carry in, if you see, it's exactly like a AND. So with that's logical function is A and B. We have a logical expression, and we can just make a digital circuit out of it. There is a XOR gate, there is a AND gate. We can just connect A and B and get Y and Z. This is 1-bit half adder. Now what about full adder? We have truth table again, right? And we can write its SOP form of the regular expression for the output Y, and also carry out for this. And then we can deploy our K-map. But in this case, K-map doesn't help because it is not going to be grouped into like more than one element groups. So it becomes almost like we are our own to reduce it. And we are trying to reduce it in terms of XOR. We know somewhere in the half adder there is an XOR, and if we can express this, then possibly we can construct the circuit, full adder circuit out of the half adder circuit. But nonetheless, we just trying to express them in terms of like some known gates. They are not, may not be basic gate. XOR is not basic gates. What we do here, we basically write down its expanded SOP, and then we are basically grouping the CI bar A bar B and CI bar A B bar, and other is CI A bar B bar and CI A B. And by definition, A bar B or A B bar is XOR, so it is CI bar A XOR B, and A B plus A bar B bar is basically A XOR B whole bar. Okay, why so? So if A XOR B is A bar B plus A B bar, then its complement function, which is like XNOR function, would be or must be its AB or A bar B bar. Just we combine the other terms, other possible min terms. So for two variables, I have possible 4 min terms, right? And A XOR B function already picked up 2 of them, min term A bar B and A B bar. So what else other min terms are? A B and A bar B bar. So if I want to do a complement of the function of XOR, which is XNOR, then I must pick up these other 2 min term, A B and A bar B bar. That's A XOR B whole bar, right? It is A XNOR B. Now you think A XOR B as one single term, like maybe T, right? So this line 3 is basically CI bar and T, or CI T bar. which is again, that means this is Ci bar XOR T, and T, as I assume, is a XOR B. So it is Ci XOR A XOR B. Okay, so we come to this term. However, the next one we have some possibilities of grouping, and we group them and make them like CIB and CIA and AB. Now from here, I am trying to write it as CIA or B, AB. However, from these 2 to 3 is kind of counterintuitive. What we did in this transformation, you cannot make it possibly directly from 2 to 3 by using identities. What we must look basically, instead of grouping of 5, 6, okay, and 6, 7, that's what it gives CIB and CIA, right? Instead of that, I am picking up 5 and 6 as it is. So term 5 and 6 is practically your CI A bar B, or the term 6, mean term 6 is CI A B bar. So I'm grouping them, making it CI A bar B or A B bar, which is basically an XOR. So why I did that? So that I can reuse an A XOR B from my summation circuit, like Y circuit. All right, I can have that XOR and plug it into my CO. That way I don't have to use other digital components there. Okay, I can reuse some of the logic evaluated already in the equation Y. So we have Y is CI XOR A XOR B, and CO is CI A XOR B or AB. Now you see, your one half adder gives you A XOR B and AB. Like I need these two terms, AB, A XOR B. From one half adder I am getting it. And then if I feed in another half adder 2, with the output from half adder 1, okay, so that XOR inside half adder 2 will give me CI XOR A XOR B, and the AND will give me the other term, CI and A XOR B, assuming I am sending in the second operand to the adder 2 of this CI carry in. Okay, so that become your CI A XOR B, and these two carry out from half adder 1 and half adder 2 must be ORed. That's what the carry out, final carry out is. My carry out from the half adder 2 is CI and A XOR B, and half adder 1 carry out is AB. So I must be ORing them together to make my final carry out of this full adder. So this is how we pick up, we use two half adder circuit and make a full adder circuit out of this fashion. Okay.